Hi, I'm Nick Moffat with Verisurf Software. Today I'll show you how the API Radian tracker is used with Verisurf metrology software to align, inspect, build, analyze, and reverse engineer parts and assemblies. The API Radian is a very compact laser tracker, measuring 14 inches tall and weighing under 20 pounds. A coaxial laser mounting eliminates bending mirrors, reduces thermal errors, and improves accuracy and stability. The tracker has a measuring range of 160 meters, or 80 meters in any direction. The Radian includes both interferometer and ADM for accuracy as well as ease of use. The tracker mounts vertically, horizontally, or even inverted for measurement in tight quarters. The iVision system uses an integrated camera for automatic target location and beam capture. Finally, the Radian includes an integrated weather station as well as an internal level. These are just some of the highlights of the Radian hardware. Next, we'll look at the software. Verisurf's metrology software is built on a CAD platform, giving it full CAD design capabilities. CAD is required for reverse engineering, but it's also very helpful when inspecting complex parts. For example, we can analyze the model, we can pull dimensions from the model, we can even manipulate the model. In addition, CAD tools such as colors, levels, and attributes allow us to manage large part assemblies. Verisurf integrates design, inspection, layout, analysis, and reverse engineering all into a single application. Finally, Verisurf is designed for both print and model-based workflows. I'll continue by loading a model of our demo part. Verisurf reads all popular CAD files, CATIA, NX, ProE, SolidWorks, etc. in their native format. This avoids the limitations of neutral formats such as STEP and IGES, which Verisurf also supports. When we open a native file, Verisurf saves it in the MCX format and leaves the original file intact. All the data, including the model, the measurements, the reports, and the analyses, are stored in a single file to simplify handling and to prevent data loss. I'll select the MCX format and open our demo part file. The part is in place and the model is loaded. In the next step, we'll align the Radian tracker to the part. After we load a model, we typically align the device to the part so we can get real-time feedback on tolerance condition. We'll use auto-align since it's the easiest way to align to a model. We start by placing alignment targets on the model to control the orientation of the part. Since the Radian is in front of the model, we'll place the alignment targets where they can be seen on a clear line of sight from the tracker. I'll start by selecting an appropriate graphics view for the targets. I'll then choose Create Target and place alignment targets on the top, front, and side of the model. Since I want the graphics view to match the camera view, I'll restore the original view. Before I run the alignment, I'll edit the targets and enable Use Smart Point. When we use the Smart Point measuring method, Verisurf records the target when I hold the SMR stable on the part. I'll run Auto Align and measure the targets as they're highlighted. When the final target is measured, Verisurf aligns the device using a best fit and shows the results dialog. We can review the results and modify the fit if necessary, but since the results look good, we'll choose to accept the alignment. When we do, Verisurf runs Inspect Build mode so we can verify the device alignment. The small deviations we see as I move the SMR around the part indicate a good alignment between the part and the model, which shows that our alignment is correct. This final check validates the whole auto-align workflow because it shows we had the right part, the right model, and we didn't make any mistakes measuring the part. Auto-align is a very powerful tool for model-based alignment, but it's easy enough for beginners to use, and the results are easily verified using Inspect Build mode. The Radian is now aligned to the part. In the next step, we'll check surface profile. In the previous step, we used Inspect Build mode to verify our device alignment. Inspect Build is a special measuring mode that displays in real time the deviation between a part and the corresponding features in a CAD model. When we're inspecting a part, the deviation reflects the material condition. When we're moving a part into position, the deviation shows us how far to move and the arrow indicates the direction. Since the Radian is already aligned to the part, when we check profile, we'll assume the deviations are due to errors in machining of the part. I'll continue by measuring deviations in single point mode on the top of the part. Notice how the deviations are represented using an arrow and deviation text. Next, I'll switch to continuous mode and scan deviations around the part. When I press Escape, Verisurf creates an analysis object in the data tree. If I highlight the analysis, we can see the distribution of deviations in the color bar. If I double-click the analysis, we can change the way the deviations are displayed. For example, we can add borders to the text, we can switch from lines to spheres, and if we enable Use MBD Tolerance, Verisurf analyzes the data to the tolerance callout for each surface. Otherwise, it uses the global profile. I'll restore the original display and then save the results. Next, I'll annotate the deviations using balloons. I'll apply balloons to 10 random points. If necessary, we can manually rearrange the balloons. I'll save the results, highlight the analysis, and create a report. I'll rearrange so that the screenshot is on top. Then I'll access Settings and change the logo from Verisurf to API. We have a number of output options, including PDF, HTML, Excel, Word, etc. I'll leave it at PDF and create the report. When the report opens, we see the API logo in the header of the report. We see the annotated deviations in the screenshot, and we see the details in the body of the report. We've just seen how to use real-time deviation analysis to check surface profile. In the next step, we'll use it to position our demo part. When we use build mode to position a part, we assume the form of the part is good and the deviations are due to errors in the position of the part. We refer to this use of real-time deviation analysis as build mode because it's often used to build fixtures and assemblies, but we can use it anytime we want to position an object in 3D space. We'd normally start by aligning the device to the basis of the CAD model by measuring features with known CAD values. We did this in auto-align. We'd then build parts into position by moving them to their nominal locations. Since the API tracker is already aligned to the basis of the CAD model, we'll simply move the part and build it back into position. I'll select and build to circles first because that's a quick way of getting the part close. I'll place the SMR into one of the holes and move the part in the direction of the arrow. This is just to get it close, so I won't bother using a pin nest. I'll then move to a second hole, repeat the process, and try not to move the first hole. When I'm close, I'll cancel the selection, display MBD, and build to surfaces to get it closer. I've enabled Use MBD Tolerance so we can use Surface Profile to control the build tolerance. In other words, as long as the surfaces are located within their profile tolerance, we'll consider that the part's in the right location. I don't have to get this to 0, I just want to get it within tolerance. It's green everywhere, so we'll call it good. This is a very simple example of a build application. Positioning a part in 3 dimensions is much more complicated, but the process is essentially the same. We've now positioned the part within tolerance. I'll tweak it a little bit for our next step. We've used Inspect mode to check our part in real time. In the next step, we'll perform a similar analysis, but we'll start by measuring point clouds. I'll begin by running Inspect mode to verify the device alignment. We know the part is good because we've already inspected it, and we know the alignment's bad because we left it that way at the end of our build demo. I'll switch to point collection and scan point clouds around the part. We're not getting real-time deviation analysis, we're just collecting raw probe center data. When I'm done measuring, I'll press Escape and highlight the Analysis tab. I'll select the point clouds and choose Analyze. The results are similar to what we saw in Inspect mode, but the deviations are much larger because of our intentional misalignment. I'll hide the analysis, select the point clouds, and run Best Fit. I'll start by running a baseline analysis. When the fit is complete, the results show the part is good, similar to what we saw in Inspect mode. I'll choose OK and apply the Best Fit. If I toggle between the before and after Best Fit, we can see the improvement. I'll select the Measure tab and run Inspect mode. We can see from the small deviations that the Best Fit is applied to the device alignment as well. Inspect mode, which we saw earlier, and Analysis, which we just performed, are very powerful tools for model-based inspection. Next, we'll measure and analyze prismatic features. All of the workflows we've seen so far have been model-based. We've aligned to a model, we've inspected and analyzed to a model, and we've built to a model. Next, we'll discuss print-based inspection and reporting of prismatic features. I'll align to the part frame shown here, but since we're not using a model, I'll open a new file. I'll start by measuring a plane in 2 lines for our alignment. Next, I'll run feature align. We can see that the origin is located at the intersection of the two lines, so our data is aligned correctly. If I place the probe at the origin, we can see the device is aligned as well. I'll continue by measuring features, starting with the large hole. Next, I'll measure a slot. I'll measure the 4 holes at the corners as though they were a hole pattern. Finally, I'll switch to point mode and measure the recessed plane on the top of the part. I'll then switch to continuous mode and scan the plane on the left end. I can fit the 4 points on top to a plane, and I can do the same for the point cloud. At the beginning of the presentation, I mentioned the use of API's iVision for beam capture. Before I finish this section on measurement, I want to explain how that works. If I break the beam, I simply point the SMR back towards the tracker. The built-in camera automatically locates the target and the tracker resets the distance. I can then continue measuring. In addition to beam capture, iVision also supports other API accessories such as the i360 probe. All the features we've measured so far are displayed in the data tree. If we highlight a feature, we can see its characteristics such as shape, size, and position. If we highlight 2 features such as 2 points, we can see the distance between them. If we select 2 circles, we can see the angle and distance between them. We've seen how Verisurf and the API tracker measure prismatic geometry. Next, we'll see how to analyze and report the results. We briefly saw the report manager when we reported our inspection results. Next, we'll take a closer look as we analyze and report our measured features. For this report, I'll select the planes and the circles of the hole pattern. When I choose the Reports button, the features are displayed in the Report Manager. If I highlight a feature, we can see its characteristics in the Details pane. We use these fields to enter the nominal and tolerance values. I'll enter the nominals for Circle 2 so we can report its position. The toolbars allow us to add nominal features, to construct features, and to add GD&T callouts to the report. I'll use them to construct the plane and then the circle through the hole pattern. I'll start by selecting the circles and then choose Construct Plane. With the circles still highlighted, I'll choose Construct Circle to create the center of the pattern. I'll then rename it Center. I'll construct lines from the center to circles 2 and 3. I'll then select the lines, calculate the angle between them, and enter the nominal value. I can calculate the distance from the center to circle 2 and enter its nominal value. I can select the two top planes and calculate their parallelism. And I can select the top plane and the end plane and calculate their perpendicularity. Finally, I'll report the position of circle 2. I want only the final values for the report, so I'll highlight them before I create the PDF file. When I open the report, we see the API logo in the header, and we see the details in the body of the report. This is a very simple report, but it demonstrates constructions as well as the use of GD&T. Earlier, I referred to the measurement, analysis, and reporting of prismatic features as a print-based workflow, but it works equally well, if not better, with a model. For our final example, we'll look at reverse engineering. Verisurf's reverse engineering tools enable mixed modeling with prismatic features, meshes, NURB surfaces, and solids. Moreover, we can take advantage of the many CAD tools inside Verisurf. For this demo, I'll scan and then surface the top of the demo part. Since the part has tooling holes, I'll begin with a simple 3-point alignment. I'll open a new file and measure the 3 points for the alignment. Next, I'll run 3-point align, fit the data to the screen, and accept the alignment. I'll continue by scanning the top of the part. When I'm done measuring, I'll press Escape, select the Reverse tab, highlight the point cloud, and choose Patch. The parameters allow us to control the accuracy and complexity of the surface. I'll verify that the probe offset is correct for an SMR, and then create the surface. When the results are displayed, we can see the values are in range, so we'll accept the surface. We now have a surface that the parameters indicate is good, but how can we check the results? On the Measure tab, we can run Inspect and compare the surface to the part. On the Analysis tab, we can analyze the point clouds to the surface. Since the data from the Radian is traceable, we have a way of proving the accuracy of our surfaces. This is a very powerful capability of an integrated metrology platform. This was a very simple example of reverse engineering, but it shows how easy it is to create and to verify CAD surfaces. That concludes the demonstration. I hope I've given you a good appreciation for how Verisurf metrology software enables the API Radian tracker with a complete set of model-based tools for alignment, inspection, tool building, analysis, and reverse engineering. For more information or to schedule a demonstration, please call us at 888-713-7201 or email us at sales@verisurf.com.